Thank you, Yuta, for the introduction, and Joe for the talk on vergence accommodations conflict and setting up the problem for us. But I still have to go through the problem statement because I'm going to be talking about it from an optics and displays point of view. So I want to share with you a new approach that we have for addressing one of the key limitations in current generation AR and VR displays. Consider today's VR displays. You have a display panel and a set of magnifying lenses, and the virtual image that is formed as a result of these two is at a fixed depth. But the virtual world that we want to represent occupies a much larger volume and depth. Since we have two display panels, one per eye, we can render the virtual world from different viewpoints and display correct parallax in each of the display panels for the eyes. And this would be a sufficient solution if our eyes were a pinhole camera. But because of our finite aperture, we are going to collect rays from multiple points in the pupil. And in order to bring the virtual world into sharp focus, because the virtual image plane is at a fixed depth, the eye is forced to focus at that virtual image plane. So this creates a conflict where your vergence cues tell you that objects are at different depths, but your accommodation cues tell you that the object is at one fixed depth. The solution to this would be a display technology in which light rays originate from the different depths for both the monocular and binocular focal cues. So our approach to creating such a display technology is to use a very high-speed display and present images across the entire volume in a very fast manner. Before I dive into the details of the display, I want to give you an idea of the dimensions of the volume. So this is the lab space that was used. The display is on the right-hand side, and the far wall is on the left-hand side. And the distance between these two is about 4 meters. And our display is capable of presenting imagery across this entire volume instantaneously. So we start with using a DMD projector. A DMD projector basically has many digital micromirrors, about 1 million of them. Each one of them corresponds to a single pixel, and these pixels are either on or off. When it's on, the light from the projector lamp is reflected into the projector lens, and it goes into the real world in order to be seen in one of these projectors. And when it's off, it just basically gets absorbed by a light absorber in the projector. So at any instant, the DMD is always presenting a binary image. And the color image is generated by binary modulation and by relying on persistence of vision. And these DLP projectors, they can be updated at like several kilohertz. Our projector updates at 17 kilohertz. That's 17,000 binary images per second. To this projector, we add a focus-tunable lens at the output of the projector. A focus-tunable lens is basically a liquid lens whose optical power can be controlled electronically. And we drive the focus-tunable lens in a continuous mode. So it constantly sweeps the virtual image plane back and forth. And we drive it in a predetermined periodic waveform, like a sinusoidal or a triangular waveform. The DMD projector and the focus-tunable lens are synchronized so that a virtual image plane is swept across the entire volume. And since the DMD projector is much faster than the focus-tunable lens, at any instant of time, we can change the projected image and build a color volume over time. So the lens frequency determines the overall display's frame rate, which we fix to 60 hertz. And the DMD frame rate is around 17,000, but we, just for a clean number, we kept it at 16,800. As a result of this, we can get 280 unique depth planes across the volume. So, by the way, we also modified our DMD projector to use a high dynamic range LED, and we will come to why this was an important step in this project later. So these are examples of some binary images that can be seen. The legend on the right basically shows you the relative positions of the virtual and real objects. To the right-hand side of that axis is real-world objects like a stamp and a textbook and garden gnome. And on the left-hand side is the virtual object, which is in this case a teapot. So in this image, the teapot is being displayed close to the viewer's eyes or the camera, and the camera is allowed to focus nearby or far away manually. While this camera is focusing near or far away, the display has those 280 images being displayed continuously, but only one of those 280 images has the image of the teapot. All other images are just black. So this kind of gives you an idea of how sharp or blurred the images would be when the display and the camera's focus matches or doesn't match. Here's another example where the display is now presenting the teapot far away, and you have the same situation where the camera is focused near and far. But remember that these are binary images. So the question is, how do we decompose a 3D scene into binary images? We do it in two steps. One is to convert the 3D scene to a color volume, and then a color volume to binary volume. So the first step is very easy. We just assume that we have opaque objects in the scene, and we export an RGB image plus depth map from OpenGL, and we quantize the depth map. This is a linear depth map. We just quantize it into the 280 depth positions. Going from the color volume to binary is more involved. So the main idea is that the binary voxels that represent a single color voxel can be distributed along perspective projection lines, and as long as they're sufficiently close to the initial color voxel's position, the eye would perceive it to be coming from a single location. And also, the binary representation for this color voxel can begin and end at arbitrary depths and in an arbitrary order. I'll give you examples of how we do this later. So these main ideas can be implemented in several different ways, and we will go through an example of how we implement. So one way of doing this is to fix the LED illumination. So we drive the LEDs in a color sequential manner, and for each color we also step through a cycle of intensities. So basically, if we assume that we have 2 bits per color imagery, then we step through like 1 intensity of red and then twice the intensity of red for each color. And this is another example when you have 4 bits per color imagery. So let's see how we use this. Assume that you have a single pixel in a color volume, and assume that you have 2 bits per color. So, and let's say that this voxel that we want to represent is 2 green, 2 red, and 0 blue. So the binary representation for this voxel is given here, and the corresponding binary volume will look like this. So basically, we chose the nearest 2 red and 2 green for this voxel. And when you have another voxel that's nearby, then you can represent in a different location. This is an example of where the binary representation for the color volume does not need to start and end at fixed location. It can happen in arbitrary orders and arbitrary locations. So going back to the initial scene, the entire scene is decomposed into this binary volume. But this illustration just assumes that we have 2 bits per color, whereas in our actual implementation we have 8 bits per color. And we also implemented this algorithm cyclically. So by implementing it cyclically, we were able to get the color volume and the binary volume to have the same resolution. However, because the binary voxels that represent a single color voxel are distributed in depth, there's going to be a blur associated with each color voxel. And this was analyzed theoretically, and we found it to be lesser than the most accepted value for acceptable depth blur, which is around 0.3 diopters. Our maximum possible depth blur is 0.16. And there's also, it turns out that as you sweep the lens, the binary volume also, as you sweep the lens, it also turns out that the virtual images are magnified differently for different depths. So there's also going to be a blur in the perpendicular direction to the optical axis. And this can result in a spatial blur. And we analyzed this also, and it turns out to be less than a degree, so it's not too much to worry about. But when you display long objects, especially towards the periphery of the field of view, you can see that long object curve away from the display. So I want to mention what are the key differences between what folks were doing before and what we're doing. Before, the same focus-tunable lenses were being used, but they were being stepped through a discrete set of focal powers. So because these are liquid lenses, for each focal state, you would have to wait for the lens to settle down, and then you would display a series of binary images that represent the color image at that location. And these approaches used a constant illumination. So basically the lamp was always on, and all the building the color imagery all relied upon dithering or binary pulse modulation at the DMD. Whereas in our approach, we continuously drive the focus-tunable lens, and we use a different illumination per binary frame, and we decompose the color voxels on a per voxel basis. So as a result of this, the color images are not only split into multiple binary images, but each binary image also contributes to multiple color images. So these are some numbers from comparing from this previous paper, which implemented a DMD-based multifocal display. So they had 6 depth planes, whereas we have 280, but their depth blur was 0 diopters, whereas our depth blur is 0.17. And so the key takeaway is that for a small penalty of depth blur, we are able to achieve a way more number of depth planes. And this is a good thing because, as the graph here shows, if the focal separation between 2 consecutive depth planes is large, then the spatial resolution of the content that is in between those focal planes reduces a lot. So it's helpful to have more depth planes, basically. So I will now show you a simulation of how our rendering pipeline looks. On the top left, you have a single color slice. So these numbers basically indicate the frames. They will go from 1 to 280. And on the right, you have the binary volumes color slice, binary volume slice. And here's the time integrated perceived image that is being built over a single frame, over a single cycle of the lens. So we implemented a display in which we can show a static image. All of the implementation for decomposition of the 3D scene to the binary volume was done offline. And the images were uploaded to the display driver, and the LED illumination and the display driver were basically controlled from a microcontroller. We cannot show videos, but we can show static scenes in which there is a lot of depth information. And as I told you before, the lab space is just the same image. So here's a video that shows our display in operation. So the legend is again the same. You have the legend where the icons on the right indicate real-world objects like the duck, the Rubik's Cube, and the poster, whereas the left objects are the virtual objects, and the distances are indicated here. So while this video is playing, the only change that's happening is that the camera's focus setting is being changed manually. The display does not have any knowledge of what the camera is focusing at. So what this means is that if you are looking through this display, you can instantaneously change your accommodation power and the image that you want or expect to be there. And the flicker that you see when you go through this display is not visible to humans. This is happening because the display's frame time is slightly shorter than the camera's frame time. So basically the camera integrates a little bit more than 280 frames, and so you end up with one bright frame every once in a while. So I want to show you another example where the image that the virtual object that we're displaying is a continuous object. It is because of this video that we call our display a volumetric display, because the previous video, people with other multifocal displays could have also done. It just requires 3 depth planes. Okay. So some of the limitations of our approach are that it's kind of a bulky form factor for now. We are positive that it can be made into a moderate form factor, and one example that I want to point out is Avegant displays, which also use a DMD chip in their display. Getting to a smaller form factor than moderate will be a challenge, but that's a challenge for any near-eye display that uses a DMD or LCOS projector. And we also have a non-zero pixel blur along depth. This is more fundamental to the approach itself, and there may be ways to mitigate this if you consider content adaptive decompositions. Yeah, and the computation cost may increase significantly if some of our assumptions are changed. Like for example, we assume opaque objects, and we assume that the field of view remains constant throughout all the depth planes. Well, the future work is that we could explore content adaptive decompositions, which with LEDs having more than just red, green, or blue, like you could imagine yellow or purple illumination, like whatever makes sense for that particular depth. And we can try to see how far we can take this display to photorealistic imagery by considering transparencies, reflections, and fog effects. And we can also integrate this with the previous work in low latency, which was done at our group, and Henry spoke about this a little bit in the morning. And the last one that we could do is to try to see how compact we can make this display. Thank you for your attention.
Okay, exciting talk, Kishore. So, questions? Or maybe I first start, because it's quite exciting.
Sure.
I'm curious if you use like other base colors, because you have now RGB LEDs, right? And
Yeah.
if you add like a white or like a mixture, do you think it make it better?
Yeah, it would definitely make it better. In fact, we could also think of having just an optimization-based decomposition algorithm. So if there's a person's face that you're trying to depict in the scene, and the face is typically of a different color than just red, green, and blue, clearly. So we can have a single color for that particular plane and be able to depict. Basically, you don't have to decompose it into many primary depth planes.
Thank you.
That's definitely possible. Oh.
Hello.
Hi.
Nice talk there, thank you.
Mm-hmm.
So I have 2 questions. So is there a relation between number of depth frames that you have to the depth blur?
Yeah, there is definitely. So the depth blur that we calculate is just a weighted standard deviation, assuming that all pixels are on. Okay?
Okay.
So because we are using 8 bits per color, and you have 3 colors, so this the pixel is being spread out into 24 depth planes.
Okay.
But assume that you want to have all the pixels on. We have a high dynamic range LED. We have 16 bits per color at every single frame. If you wanted to really show that bright of a white color, you would just send the maximum possible number to it.
Okay.
Yeah. So it will definitely help to, like, think of a different decomposition algorithm.
Okay.
Yeah.
Next question is, what's the perceivable difference in, in the image quality with 280 depth planes versus 140 depth planes, right?
The image quality measured in terms
Of, let's say, depth blur itself, for
measured in
example.
terms of depth blur. I think that it's first of all kind of difficult to measure depth blur. And multifocal displays earlier have analyzed the spatial blur that results between two focal planes, and that gives you this graph. So if you study this graph, like, this is the focal plane separation and this is the drop in spatial frequency. So if your depth separation is, like, let's say 0.7, then your spatial frequency drops to 15 from something like 60. So at that depth where the depth plane is, you have very high resolution. But the content in between those depth planes, they have some blur effects in them. So basically, the takeaway is that you need to decrease the focal plane separation a lot in order to maintain good spatial resolution throughout the entire volume.
Okay, great. Then let's thank Kishore again, and then let's move on to the next talk.